Okay, here we're going to look at Module 3A. Module 3A deals with liquid properties, ideal gas properties, and energy as a relative property, relative to some place we call zero. First we'll look at compressed liquids. Now, compressed liquid is one where the pressure is higher than the saturated pressure for a given temperature, also called a subcooled liquid. Sometimes you have compressed liquid tables, and if you have that data, definitely use it. But many times you won't have that data, so you have to make an approximation. Here we can recognize that liquid properties are primarily a function of temperature. So here we have primarily a function of temperature and a very small function of pressure. So we can use the saturated liquid values at a given temperature and ignore the pressure effect on the liquid, particularly for properties like U, V, and S. Now, where are liquid properties listed as a function of T? Again, in your saturated tables, you have a temperature table. Go there and look up the values for the liquid and ignore the pressure. You're going to get a small error, but in many cases it'll be just fine for what you're trying to do. Definitely make sure before you use the liquid properties from the table, you make sure you're working with the liquid. So we'll have an example of how to determine that in just a second. Okay, let's take water at 25 bars and 100 degrees C. Try to find what the volume is. Well, you know at 25 bars that's much, much higher than 1 atmosphere. That's nearly 25 atmospheres. A bar is close to an atmosphere. And you know that water would boil at 1 atmosphere at 100 degrees C. So 25 bars, definitely a compressed liquid. Go to your compressed liquid tables, and the volume of water is 0.0010423 meters cubed per kilogram as a compressed liquid. If you look up the saturated liquid value, you see it's very, very close. In fact, there's only a 0.1% error between those two values. So it's a very good approximation, even at a high pressure of 25 atmospheres, to neglect the effect of pressure on the volume of a liquid. We say liquids are nearly incompressible, so the volume doesn't change. Let's take another example. Let's suppose now we have water at 100 bars and the volume is 0.00119. We want to find the temperature. Well, first we've got to determine, you have two properties, T and P. First you have to determine the, let's say, the state of the substance. Is it a liquid, a vapor, or a mixture? So we look at 100 bars at the saturated value, saturated liquid value, and find that our volume is lower than that. So we know we're in the region where it is a liquid. At that point we say, what temperature gives us this volume of 0.0119 or 0.00119? Searching through the saturated liquid tables, you'll find that that volume occurs at a temperature of 220 degrees C. So you conclude that knowing that it's a liquid and knowing that that temperature gives you the volume you have, the temperature must be 220 degrees C or something close to that. Now let's look at the enthalpy of a liquid. Now in enthalpy you have to be careful, particularly when you're dealing with pumps, and often this comes up with a pump where raising the pressure is the most important thing. Now the enthalpy, you recall, is U plus PV. So here we have U saturated plus P times V saturated, and here we use, instead of the saturated pressure, we use the actual pressure. That should give us something a little bit closer to what the H of the compressed liquid is, because we're making the approximation that U saturated represents the internal energy, and adding on the PV term, but this time using the P of the actual P rather than the PSAT that you'd find from HF in your tables. Another way of doing this is to take the H saturated and correct for the increased P by multiplying times the actual P minus PSAT, which is where the HSAT is listed, and multiplying that times VSAT, assuming that the volume isn't changing over that interval. And as we saw earlier, liquids are nearly incompressible and the volume is not going to change much at all. So now suppose we want to find the enthalpy change of a liquid with respect to temperature. We can just use Cp. This is a good approximation for temperature change on enthalpy. Just use Cp of the liquid times delta T. Now I recommend that you go to your tables and look through your book and find out what values Cp are for liquid. Now liquid has a very much different value of Cp than a gas does, so you don't want to mix those two up. Go and look at the Cp of water as a liquid, the Cp of water as a gas. Compare those two so you get a feel for it. Also, you'll find all kind of other fluids or liquids where you can find Cp data for that in your book. So take a look at those tables. Try to get familiar with them so you'll be able to go to them quickly and find this data. Okay, now let's look at the properties of ideal gases. You recall an ideal gas is PV equals nRT. Ru is the universal gas constant. Another property of ideal gas is that the energy is a function of temperature only. Now remember, we said there are two properties to define a state, but in the case of ideal gases, the energy really only requires one property to define it. That's the internal energy, and that's temperature. Now we want to know, when do we have an ideal gas? When is a gas ideal? Well, gases are ideal when the molecules are far apart or the volume per mole is large. You have a very large volumes. And in that case, the intermolecular forces are negligible and the gas will follow the ideal gas law and behave as an ideal gas. I know when practically is a gas ideal. So we pull up the ideal gas equation, V equals nRT divided by P. And from that we can conclude that ideal gases occur when you have a high temperature, because in the numerator you'll have temperature and that'll make your volume large, or a low pressure, because in the denominator you'll have pressure, and a low pressure will make your volume large. Have low intermolecular forces, low interaction amongst the particles, and you'll wind up with an ideal gas. Now we want to say that what is high and what is low is a relative concept relative to the critical temperature and the critical pressure of the gas. And we talked about critical temperature and critical pressure earlier. So there's a theory that all gases behave in a similar manner when compared to their critical temperature and pressure. So high temperature for steam would be much higher than high temperature for something like nitrogen, where the critical temperature for nitrogen is like 126, something like that, degrees Kelvin, whereas for steam it's above room temperature. Critical temperature for steam is, oh gosh, 705 degrees Fahrenheit, pretty hot for steam. So those what you call high temperature and high and low pressure depends on the gas that you're talking about, or the substance that you're talking about rather. Now for engineers, we take another look at the ideal gas equation, and we like to use mass instead of moles because we're constantly weighing things out and producing mass, or producing substances and weighing it based on the mass, not the moles. So we like to use mass, so what we'll do is redefine this equation as PV equals mRT, where this new R, let's see, the new R is actually the Ru, the universal gas constant, divided by the molecular weight. And often engineering textbooks will use this R. The only problem is there's a different R for every gas. I personally like to just remember this equation as PV equals m over molecular weight RU times T. That way I can work the mass in there. The moles are m over molecular weight, and all I have to do is remember different molecular weights. I'm a chemical engineer, so it's no big deal for me to remember different molecular weights. For instance, O2, oxygen, is approximately 32, N2, 28, water, H2O, 18. I'm not going to remember as many values of R, where it's RU divided by the molecular weight. That just doesn't stick in my head. But you can use it either way. Just be careful, watch your units, and your calculation should come out okay. Okay, we want to talk about energy changes now. For an ideal gas, du is equal to CV dt. Again, only a function of temperature. Now dH, remember H is U plus PV, so dH is du plus d of PV. And so we can add that together, and if you call for an ideal gas, PV is equal to RUT over molecular weight, so du dH is equal to du plus d of this quantity here in the brackets. Now the only variable in that quantity is temperature. So we can take this out and say that du plus R over molecular weight times dt will give us dH. So in fact, we wind up with dH equals CV plus RU over molecular weight all times dt, which just allows us to calculate Cp. Remember, dH is equal to Cp dt, where Cp is equal to Cv plus Ru over molecular weight. So the thing to remember is that if you have values for Cp, you can get values for Cv from this equation here. Easy to go between Cp and Cv for an ideal gas. Now, if we want to calculate a total change in energy, we really have to integrate. What I haven't pointed out too much in the past is that Cv itself is a function of temperature. So it's changing with temperature. If you have wide swings in temperature, then you have to integrate it. Over a small interval of temperature, you can say Cv is approximately constant. Take it out in front of the integral, and then you'll just have Cv delta T. So in this case, for small change in temperature, Cv, the integral of dt, is Cv times delta T. We're assuming here that Cv is constant. For delta H, instead we use Cp. We have the same type of calculation. For small delta T, Cp times T2 minus T1 will give us the change in H. Cp is assumed constant in this case. For a large delta T, you'll often see, and in fact in your text, and in any good engineering text you should find, engineering thermotext, you should find CPs listed as a function of temperature. And this, what we have here, is called an empirical equation. This is value, we're giving a polynomial of t, fitting the data for Cp to t with various constants a, b, c, d, and e. And you'll find those listed for various gases. In many tabulations we'll list Cp values as a function of t this way. Polynomial in t, in which case you have to integrate it, which is a fairly simple integral to do. Delta H then is the integral of Cp dt. Typically you'll see Cp values listed. You won't see Cv values listed, but you know for an ideal gas you can just subtract R over molecular weight and you can get Cv from Cp. Now the last concept I wanted to talk about in this module is that energy, or enthalpy, is relative to some reference state, some place that we call 0. So, I want to talk about different types of energy changes. One is a latent energy change. And latent energy change means the structure is changing. So it's changing from a liquid where it's very dense and close into a gas, and you have a phase change with that. Another is a sensible energy change where the temperature is changing. So the changes we've been talking about so far, the CPdT and the CVdT, those are sensible energy changes. Latent energy changes are very large often, and going from liquid water to vapor water takes a whole lot of energy, even though the temperature may not change. So that's latent energy of a phase change. Okay, in this slide we're going to look at these energy changes. Here what we'll call delta H1 will be the sensible energy change of the liquid going up to its boiling point. Delta H2 will be the energy of vaporization going from a liquid HF to a vapor Hg. And here we have delta H3 will be the sensible energy change going from the vapor, saturated vapor, to a superheated vapor at a higher temperature of 200 degrees. So delta H1, the first calculation, is Cp of the liquid times delta T going from 0 on up to 100 degrees C. Cp delta T. And that's the change. You're starting from 0, H is 0 at your reference state. So the enthalpy that you calculate here will be HF at 100 degrees. From this point, HF to Hg is simply HFG. And so this H right here will be HF plus delta HFG or HFG. And finally, raising on up to H3, which would be a superheated vapor at 200 degrees C and 1.013 bar, or 1 atmosphere. This will be the entry in your superheated table. If you add up all those delta H's starting from the 0 point up to this point here, you'll get your actual H in the table, and that's how it's calculated. So at 0 degrees, saturated liquid H is approximately 0. And let's take delta H1 as Cp of the liquid delta T. Cp of liquid water is approximately 4.184. All the way from 0 to 100, it doesn't change a whole lot. That's a fairly small temperature change. And so the enthalpy, just as it's about to boil, should be approximately 418.4. Now, once you reach the boiling point, you have to add on that heat of vaporization, which is Hg minus Hf, and you may recall that we call that HFG. That is a very large amount of energy, 2257 kilojoules per kilogram. And then to raise it on up to 200 degrees, delta H3 would be Cp delta T for the vapor. Now notice that the vapor Cp 1.979 is much lower than the liquid Cp 4.184. If you add all those together, then you should get the enthalpy relative to that point we called 0. And if we look at the tables, what we had versus what we calculated, H1 would have been 418 calculated versus 419 listed in the table. Some small error there. H2 would have been calculated as 2675, and H3 would have been 2873.3 calculated. So again, delta H1 is raising the temperature of a liquid, delta H2 is vaporizing the liquid, and delta H3 is raising the temperature of the vapor. So if you have a substance and you don't have tables, say methanol or butane or something like that, you have to find the enthalpies Often you won't have tables, so you'll have to use this data on heat of vaporization and CP and for the liquid and the vapor to find your enthalpies. Okay, let's talk about liquid properties. Again, recapping what we did. We said that liquids were a function primarily of temperature and a small function of temperature. So we can use the saturated tables to estimate the liquid properties, but we will correct H for the pressure. We looked at ideal gas properties, PV equals nRT, and the idea that du and dH were CVDT and CPDT respectively. We said that ideal gas occurs at large volumes, which, remember, specific volume is 1 over density, so either large volumes or low densities. And then we looked at energy as a relative property. Saw that tabulated entropy energies, the ones in your tables, are actually changes in energy calculated starting from a reference state. So for homework, what I'd like you to do is calculate delta H for water at 1 bar from 400 to 500 degrees and from 400 to 700 degrees Kelvin using Cp delta T, the integral of Cp dt, the tables, and the Moliere chart. So the Moliere chart is actually an HS diagram. You'll have H on the horizontal and S on the vertical, entropy on the vertical. And you'll find that Moliere chart in your book. I also put a little video out of the Moliere chart and how to find properties from it. It's very handy, this Moliere chart, so go take a look at that and